Good morning, everybody. Audio check. Anyone, please confirm me if I'm audible.
Yes, ma'am.
All right. So, good morning, everybody. This is Kashyap Seher, your host for today. I warmly welcome all of you to the second day of this workshop on characterization techniques. Before moving towards our lectures, I would like to request all of you to please don't turn on your mics and don't share your screens as well, because it automatically cuts down the presenter's video. So, we have the only option to remove you from the meeting, and we really don't want that. And secondly, I am also a PhD student in chemical sciences, and I know the worth of characterization techniques. They are the backbone of your research. So I suggest all of you to listen carefully and note down all the important points, although you would have the recordings and presentations as well. But listen carefully and focus on the words. So let's move towards the first lecture of today. I would like to invite Dr. Ashraf Ali to deliver his lecture. He is director of IM Group of Researchers. He is currently working as assistant professor in the Department of Chemistry and Chemical Engineering, Henan University of Technology, China. He has worked as a postdoctoral research fellow at Inha University, South Korea, and he has also worked as assistant professor at Department of Chemistry, University of Haripur, Pakistan. Sir, it's really an honor for us to have you with us. Now it's over to you to please present your lecture. Dr. Ashraf Ali, can you hear me?
Hello,
Hello, sir.
can you hear me, Kashyap?
Yes, sir. Yes, sir.
Okay, so Assalamu alaikum and good morning to all of you. Thank you so much for introducing me. And now I will going to start my presentation. Can you see the screen?
Yes, sir. It's visible.
Okay. First of all, I would like to introduce myself. You have already introduced me. My name is Ashraf Ali, and I belong to Swat, Pakistan. I have completed PhD from Enha University, South Korea, in 2018, and then completed one postdoc from 2018 to 2020. And then I served as assistant professor at the University of Haripur from 2020 to 2024. And then currently I'm working as associate professor at the Department of Chemistry and Chemical Engineering, Henan University of Technology. The topic which I'm going to present today is thermal analysis. These are the contents of today's presentation: introduction to thermal analysis, differential scanning calorimetry, thermogrametric analysis. We have thermomechanical analysis, dynamic mechanical analysis, and the dilatometry. But my focus will be on the first two techniques because these two techniques are most widely used in the academic research. And I think most of these participants belong to the academic research. The other three types of techniques, thermal analysis techniques, are also used, but mostly these are used on industrial scale. And the first two techniques are used mostly both in industry as well as in academia. This is the general introduction of thermal analysis. According to IOPIC 2014, thermal analysis can be defined as that the study of the relationship between a sample property and its temperature as the sample is heated or cooled in a controlled manner. So the changes are recorded and these kinds of analysis are called thermal analysis. If you look toward this diagram, you can see that a substance is subjected either to heating or cooling, and some changes happen and these changes are recorded. So what kind of changes when a sample is subjected to heating or cooling? There may be the thermal change, the temperature may increase or decrease. There may be the weight change. There may be change in the dimension, and there may be the evolution of some gases. So when a sample is subjected to temperature, and the thermal change happen. So such kind of analysis are categorized as the DSC, differential scanning calorimetry, or the DTA, differential thermal analysis. When there is the sample is subjected to change in temperature, and there is some change in the weight of the sample, so such kind of analysis is categorized as the TGA, thermogrametric analysis. And if a sample is subjected to change in temperature and the change occur in the dimension of a substance, then we call it the thermomechanical analysis. And if the evolution of some gases take place, then we call it the EGA. So the thermal analysis can be classified on the basis of these properties and the basis of these changes, like the change may be thermal change, weight change, dimension change, or evolution. And that is why we categorize all thermal analysis into these groups. The thermal analysis instrument include the basic heating unit, which may be furnace. Furnace is the most important part of this instrumentation of thermal analysis. We have a sample holder and the sensor. The heating and cooling of a sample will take place inside the furnace, and the temperature will be detected and it will be sensed by a sensor. There should be a temperature control unit because we are carrying out the change in temperature at specific rate. We can adjust the temperature, we can increase or decrease the temperature, or we can increase the temperature per unit time. And the data recording unit, which can be a sensor, and the signals are captured by the sensor, and it will move toward the analyzer and we get the results. What are the factors which should be considered for the method selection? As I have told you in the previous slide, that there are different types of thermal analysis. So which types of thermal analysis we should choose? So when choosing an appropriate method, let's suppose we are going to analyze a sample. So for that sample, we can choose a specific thermal analysis technique. Either we can use the DSC, or we can use the TGA, or we can use another technique. So which kind of factor we should keep in mind while selecting a particular thermal analysis method? So these factors should be kept in mind. The property to be determined, like which property we want to determine. Let's suppose we want to find out the properties and the dimension of material, then we should choose the specific TGA method, the specific thermal analysis method. Similarly, if we want to find out the weight loss, then we should choose the TGA method. Second one is the type of material, which kind of material we want to analyze. Either this material is compatible with this particular characterization technique or not, the temperature range, and the sample state. So we cannot randomly choose a thermal analysis method for the analysis of each and every sample. If we want to select a specific sample analysis, we should keep these things in mind, and then we should choose a suitable method for the analysis. Now, these are the selection of analysis technique. On the left hand side of this table, we have these thermal analysis technique like the DSC, DTA, TGA, and TMA. And here we have the properties which we want to measure. So let's suppose if we want to measure the melting point, or we want to characterize the material on the basis of their difference in melting point. We want to then we can choose the DSC, and we can also choose the DTA. We cannot use the TML as something like that. Similarly, on the basis of glass transition temperature, crystallization, reaction polymerization, sublimation and evaporation, pyrolysis, thermal expansion, thermal history, and specific heat capacity. The most important thing that while using the thermal analysis, we can evaluate these properties like melting point, measurement, glass transition temperature, crystallization, reaction such as polymerization, sublimation, dehydration, evaporation, pyrolysis, thermal expansion, thermal history of the material, as well as the specific heat capacity. So these properties can be checked by using different thermal analysis, which properties is suitable for which which thermal analysis technique there. So this table simply summarizes all this technique. So the first thermal analysis technique among these are the DSC, differential scanning calorimetry. DSC is a thermoanalytical technique that measure physical or chemical changes within a material in response to temperature. When a material is subjected to a temperature and there is some physical or chemical changes occur, so such kind of changes are measured by DSC. DSC provide both qualitative and quantitative information about the endothermic and exothermic process in a sample or the changes in heat capacities. So either the material will release the heat or it will absorb the heat. So we measure that exothermic or endothermic properties as well as the heat capacity of the material using DSC. And DSC, the sample can also be submitted to annealing, edging, cutting. So it means that whenever we are conducting the DSC, the sample may be subjected to these steps. It is used to determine the phase transition temperature, and the heat capacity of the analyzed sample. So DSC is also used to find out the glass transition temperature. It can also use about the phase transition temperature as well as the heat capacity of the sample. Now look toward this slide, you can see that a typically DSC instrument. On the left hand side, you can see that this is the DSC analyzer. And inside the DSC analyzer, the most important part is this cell on which we put a sample. The sample are loaded into the fan and heated at a PEX rate, a specific degree per minute. And this is very important to fix the temperature, with changes to the heat flow across the sample being recorded as a function of temperature. So when a sample is put on this fan and the temperature is fixed like 1 degree C per minute or 20 degrees C per minute, and then the heat change takes place, this is noted, recorded. The technical specification, the temperature can be used mostly from minus 170 degrees C to 600 degrees C and per the DSC analysis. And the heat of rate is about 0.1 degrees C to 200 degrees C per minute. The atmosphere, we can provide inert atmosphere using nitrogen, or we can provide the oxidation, we can provide the atmosphere which contain air for the oxidation purposes. So the atmosphere may be inert using nitrogen gas, or it may be oxidative just like air. And the required sample, we can mostly use, it will be 100 milligram of the sample will be enough. So this is the specific representation of DSC analyzer, that how it looks and how we put the sample and which vector how we should fix the temperature and what we measure. How DSC work? This is the basic sketch of the DSC working system. So the DSC chamber contain two sample position, sample and reference. Look toward this diagram. In one fan we have put a sample, while in another fan we have put a reference, because we always compare the properties of a sample material with a reference material. The reference is an inert material which have no thermal transition and the temperature range, so that the material which have no specific change in their thermal properties, that should be our reference material. The sample and reference are heated, where the sample undergo thermal transition, and the thermal transition takes place. Either it absorbs the heat or release the heat. And the temperature difference between the sample and the reference is measured by the thermophile sensor, giving the differential thermocouple voltage, which is converted into energy per unit time by the instrument using a calibration constant, and we get a curve. So the result is expressed as the heat flow rate versus temperature on one side, and the y-axis we have the heat flow rate, and on the x-axis we have the temperature as compared to that of the reference. Look toward this curve. This is the DSC curve, typical DSC curve. So how we can interpret the DSC curve? The first one is the heating curve. You can see here the curve which is shown below. And on the y-axis we have the heat flow, weight per gram, and on the x-axis we have the temperature. So first, heating curve analyze the material. Its production and failure analysis can be noted from this one. Let's suppose we have put a material and the DSC fan, and we have measured this curve. So if you look toward this curve, you can see that in this curve, after heating, we get that the temperature has been, this is the melting temperature, and it is about 128 degrees C. So this shows the melting temperature of a particular sample. Now this melting temperature will be different for a different material. Similarly, we can also measure the crystallization, the resolidification of the material. So whenever we decrease the temperature now, so decreasing the temperature up to 109 degrees C. So what will happen? This material, you can see that it solidify once again. So using the DSC analysis, we can find out the melting temperature and the recrystallization or resolidification temperature. And this temperature, melting temperature and resolidification temperature will be specific for specific material. And we can compare the two material or two different material on the basis of these differences. Now, if you look toward this diagram, this is the interpretation of another DSC results. And after the analysis of DSC, we have got this curve. So this curve provide more information. The first one is the glass. This point is the glass transition temperature, and glass transition temperature is the temperature at which the mobility of a solid material starts. So there is the difference between glass transition and melting temperature. At a glass transition temperature, the molecule loosen, but the solid material just look like rubbery or viscous material, but it has not been totally changed into a liquid form. While at the melting temperature, the solid material totally changed from solid to liquid form. So you should remember the difference between glass transition temperature and melting temperature. Now let's suppose this material has been heated up to here. So at the melting temperature of this material is about 250 degrees C. At 250 degrees C, this material have shown this curve. And remember that the area of this curve is also specific for specific material. So the properties of that material can be measured from the peak to the temperature as well as the peak area. So the peak area and the specific temperature at which this peak appear, it should be noted, and this will be related to the melting temperature of that material. Now let's suppose two material have the same melting temperature, but they have the different peak area. So we can also differentiate on the basis of peak area. And the second one, on the cooling of this material, bake up to about 150 degrees C. So this is the resolidification or the cold crystallization. So on the basis of this crystallization curve, or on the basis of this melting temperature, we can differentiate the two materials from each other. Similarly, the heat, like this peak also show us the heat absorbed or released, how much as a normalized heat. So specifically, let's suppose the curve represented in green color, it show that it is about minus 40.14 joule per gram. So this is the heat released by this materials, and this material, this specific temperature or the amount of heat released or absorbed will be different for different material. Typically, DSC curve show us that how the melting temperature of a material will be different, and how the recrystallization temperature of that material will be different for different material, as well as the peak area of the melting temperature curve, as well as the cold crystallization curve. Similarly, using DSC, we can analyze a material that either the material is amorphous or it is the semi-crystalline. So look toward this. This is the typical DSC curve for the two material. If you look toward the crystalline material, it have the DSC curve, which show the melting temperature up to here. While the amorphous material, it show the curve which have not a very sharp peak. So using this DSC analysis, we can also differentiate. We can find out that either the material is amorphous or it is crystalline in nature. Similarly, we have crystalline material, but these have we have different material. Now let's suppose in this curve we have 1, 2, 3, 4, 5, 6, 7. We have 7 different polymers, and we want to analyze this polymer by DSC. So on the basis of their melting point or melting temperature, we can differentiate that there are different polymer in this sample. Look toward the first peak. This peak appear at 130 degrees C. So this is the polymer number 1 or material number 1, which have the melting temperature of 130 degrees C. Similarly, another have which I have marked here, the melting temperature is about 220 degrees C. So this is material number 2. So in a sample, we can find out if we get one peak, so it means that there is only one kind of material or one kind of polymer. If we get multiple peaks, so it means that there are different types of polymer or different types of material on the basis of their melting point or melting temperature. On the basis of the glass transition temperature, we can also differentiate between the material on the basis of their glass transition temperature. So let's suppose the glass transition temperature for the material polymer number 1 is about 120 degrees C, while for the polymer number 2, it is about 150 degrees C. So using this curve, they have different polymer have different glass transition temperature due to different types of cross-linking and due to different types of covalent bonding and intermolecular attractive forces. So we can differentiate between these polymer on the basis of their glass transition temperature using DSC analysis. Similarly, we can also find out that either this material have some failure or not, or either this material have some contamination or not. So the first curve show the DSC analysis of a pure resin or of a pure polymer material, and you can see that here the melting temperature is about 109.98 degrees C. But if you look toward the second curve, this material contains some impurities, so it have shown us the two different melting temperature, and these two different convolution in this curve show that this material is not 100% pure and it contains some contamination. So if we synthesize the polymer material and we want to find out the property that either this material have some failure or this is 100% pure material, we can find out it by using the DSC analysis like this. Another application of DSC analysis is we can find out the molding or the curing of a material, the curing of polymer composite or coating. Curing is the toughening or hardening of a polymer material by cross-linking of the polymer. So look toward these two curves, you can see that the raw rubber it have the heat and the energy of about 225 joule per gram, while the molded rubber show the 20 joule per gram. So the curing in the raw rubber is much more than the molded rubber, and we can find out the difference between these two rubber on the basis of their energy. Now there are several limitations of this DSC. Because it is very difficult to interpret the exact DSC analysis, and sometimes a small amount of impurities may change the results. Also, the instrument and the temperature selection also change the results of DSC analysis. So there are some limitations. The first one, interpretation of the result is highly dependent upon the analyst experience. So it depends upon the experience of the analyst that how he interprets the result. Some people interpret the result this which we call over interpretation, mean that the peak do not show a particular region or particular phenomena, and a researcher explained that this curve represent like this. So always the interpretation of DSC result need expertise in this field. Otherwise, just a common knowledge of a person cannot interpret the result very well, and there will be a lot of error. Second, the technique analyze the bulk property of the sample. So it shows us different property like the glass transition temperature and also melting point, and also we can analyze all when we analyze the sample, so we can get knowledge about all these things, and that is why it is not used specifically for one for checking the one property, a single property. So that's why this it provides us the information of the bulk property, not a single property. So this is not a very highly selective technique. Selective technique means which provide the information of only selective properties, while the non-selective technique means which provide the properties, so many properties. Machine is highly sensitive, which make it sensitive to contamination or noise. So just as I told you before, that maybe there is some noise. The peak appear in the palm of noise, and the observer will be confused that either this is a peak or this is a noise. Because sometimes we see in the curve that there are some up and down due to the machine noise, and we get confused that either this is this is curve or this is nice. So we should remember that either the machine give the stable baseline or there is some noise. So we should make sure that the machine is stable and there is no noise. Otherwise, if we see a noise and then we confuse that it is a kind of peak, then the results will be not exactly which a sample is. The test method is unable to differentiate between samples that have similar melting point or having glass transition temperature. So this is also a very important point that let's suppose we have two polymer having the same melting point or same glass transition temperature, then we cannot differentiate them only by DSC analysis, because at DSC analysis they will give us the same curve, the same peaks at the same temperature. This is the limitation. Now another technique which is most commonly used for the analysis, and this is the thermogravimetric analysis or TGA. TGA is more commonly used in the DSC. This is also a thermoanalytical technique that measures the weight change of a sample at a given time and temperature. So it changed it is a thermoanalytical technique which measures the change in the weight of a sample. The change in sample weight can be owing to modification in chemical or physical properties. Now, how the weight change? The weight may be changed due to physical properties, just like the absorption of water molecule, the removal of water molecule, or the removal of some functional groups of some. If we heat a sample for a very high degree C, that may be chemical change or physical change. The sensitive microbalance measures the change in sample mass as it is heated or placed isothermally in a furnace. When we put a sample in a microbalance and any change takes place, just like we put a sample and it have absorbed water sample and it have absorbed water vapor from the atmosphere, and this water molecule removed by heating. So the operation of this water molecule will bring very small change in the weight of the sample, but this balance should be sensitive enough to measure that change. Similarly, the removal of particular functional groups or some polymer from the basic material, just like we have chemically modified silica with some organic ligand, and now we heat this silica up to certain temperature, and organic contents are removed, just like in calcination. So it will bring very small change in the weight of the material, but this balance should be highly sensitive to measure this small change. TGA can quantify the major constituent of a material, decomposition, and thermal stability of material. Using TGA, we can find out the major constituent of material, the decomposition of material, that either it decomposes at that particular temperature or not. Let's suppose we have silica or calcium carbonate or some ceramic material, so definitely they will not decompose even if we heat them up to very high degree C. Only the water molecule will last by heating these material up to very high degree C. On the other hand, if we have some composite which have organic and inorganic hybrid material, so the organic component decompose at very high degree C, just like 400 to 600 degree C, and then we can check that either this material is decomposed or not. So we can measure these properties using TGA analysis. Instrumentation of TGA. So the TGA also have a furnace and sample holder, temperature sensor, recording balance, the atmosphere control. We can provide the inert atmosphere, and we can also provide the oxidative atmosphere. Inert atmosphere contain nitrogen, and oxidative atmosphere contain compressed air. And the furnace temperature programmer, it is very important to control the temperature program, and the recorder. So these are the basic parts of the instrumentation. TGA is used to measure the thermal stability or the degradation of the material, vaporization and sublimation, quantitation of volatile and moisture present in a material, decomposition kinetics of material, that how much time it takes to decompose a material. And TGA is highly sensitive. It requires only small amount of sample material and provide quantitative and reproducible results. However, it may be challenging to determine the cause of the measured mass change with TGA alone. It does not directly distinguish between physical and chemical phenomena occur during the temperature change. A more comprehensive understanding of the material behavior can be achieved in combination with other techniques such as DSC, FTIR, or MS. That means that TGA sample is not enough to characterize the material. It provides information about the weight loss, information about the attachment of some different ligands to the surface, the decomposition, evaporation, moisture content, and so on. But it is not enough to measure all properties of a material. Now, the most important part of this technique is TGA curve, or interpretation of the results. So, what the TGA curve looks and what it show, what it represents. So, look towards if you look toward the curve, on the y-axis we have the weight percent, on the x-axis we have temperature. If you look toward the left curve, the temperature, there is as we have controlled the temperature programming, the heat we heat the sample up to 650 degrees C at a rate of 20 degrees C per minute in nitrogen. Then the sample is cooled down to 500 degrees C in nitrogen to see what happens. And then the sample is heated to 80 degrees C at a rate of 20 degrees C per minute in air. So remember that and the TGA analysis is affected by the heating temperature, heating rate, mean temperature per minute, the atmosphere, that is nitrogen or that is air, and so on. So look toward this TGA curve. At first stage, we have increased the temperature up to 200 degrees C. There is no change, there is no weight loss, and almost the weight is 100%. The curve is just horizontal curve. We have started. Now up to about 380 degrees C, there is no change. And at 390 degrees C, now the weight loss start. And the curve is dropping down. The weight is decreased. The weight of the sample is decreased. What happened here? There are different phenomena may take place, like the decomposition of some groups start, the decomposition of the material start. Now, if we go here up to 400 degrees C, then again, what happened? The decomposition of the material start and the weight loss. The weight is continuously losing. Now we have reached to this the red. You can see the red line at 630 degrees C. Again, we have started the cooling. The line goes back. This is called cooling again. Cooling from 630 back to 500 degrees C, and we noted what happened. And now again we have changed from nitrogen to oxygen. That the program is changed from nitrogen to oxygen, and now the curve, you can see that in the air at 20 degrees C, the weight loss is so high. But you can see that even at this temperature, the weight is not reached to zero. So it means that the material has not been totally consumed or decomposed. So what this curve show? This curve show that there are some material, there are some substances which are not decomposed even at 100 degrees C, and these material may be carbonate, or it may be silica, or it may be any other tough material, ceramic material like this. So the interpretation of this curve show us that what happened to the material whenever we are carrying out the TGA analysis. Now the interpretation is explained little more. On this curve, you can see that on left hand side we have the weight loss percent, on right hand side we have the derived weight of the material. So once again, if you look toward here, start with the derivative curve. Now there are two curves. The first one is the TGA curve, and the green curve is about the derivatives curve, that what we have derived from this one. Now look toward this one, the decomposition step here. The first decomposition step, and there is a second decomposition step. The first decomposition step is the decomposition in nitrogen, which start at 505 degrees C. The second one is decomposition in air, which is 600 degrees C. So if you interpret the TGA result, you can get either the first curve like this, or you can get this kind of curve. So the first curve just simply show you the decomposition of the material and the change in the weight of the material while heating at a specific temperature. While this curve show you the it also show you the derivative curve, mean which show the decomposition of the material, how much the material has been decomposed. This how much so we can see that the material has been decomposed at 505 degrees C in nitrogen, and then a second decomposition show that at 600 degrees C the material also decomposed in air. Now, this is if you look toward the residue here show that there is when the weight do not reach 100 to 0%, so it means that there are some residue, and residue are those material which do not decompose even at a very high temperature, and it may be carbonate, or it may be some ceramic material or silica, something like that. So you can find out this information that the weight loss in a sample using nitrogen up to 505 degrees C, that is about 79.12%. The weight loss in air is about 19.34%, and how much is the residue? It is about 0 point something like 0.6%. Application of TGA. So the TGA is used for the different material have different decomposition and different cooling pattern and different decomposition pattern. So that is why while we carrying out the TGA analysis of two or more material and compare these results, so we can differentiate among these material. Now look toward this curve. There are three different curves here. So the first one is the curve which show the decomposition at 300 degrees C, 350 degrees C almost, and another curve is about the 400 degrees C. So the material which and with the decomposition start later, like it started at about 336 degrees C. So it means that this region or this polymer is more thermally stable. The material, the curve at blue line at have started decomposition at 302 degrees C. So it means that this is least thermally stable. So we can differentiate the thermal stability of the material using TGA analysis. This another important application of TGA analysis, that using the TGA analysis or the TGA curve, we can find out the grafting density. That how much is the grafting density of the material. Grafting density mean that mostly we take a material just like cellulose, or we have silica material, and we carry out their surface functionalization with specific ligand. So how much the material, how much the organic ligand is attached to the surface of the material, this is called the grafting density. So grafting density can be calculated from this TGA analysis by using this formula. And we after applying this formula in a specific experiment, we have found out that, let's suppose the grafting of vinyl group is 0.92 micromole per meter square. So after TGA analysis, we get some numerical value, and putting all these numerical value in this formula, we can find out that how much organic ligand attached to the surface of silica or the surface of any other matrix material. So using the TGA analysis, we can find out that either the surface functionalization has taken place or not, or if the surface functionalization has been taken place, how much is the grafting density, or how much the ligand has been attached successfully to the surface of silica particle or any other matrix material. So this is another application of TGA. Now, how we can practically use the TGA. So the TGA can be practically used for the analysis for the differentiation of different surface group. Here I have provided one example of a research paper, surface functionalization of silica nanoparticles for enhancing the stability of dispersion. And this paper has been published in Journal of Nanoparticle Research 2014. They have taken different material. We have four types of material A, B, C, and D. Now the material A, this is just like simple silica particle with no modification or no surface functionalization. So look toward the TGA curve of this bare silica particle. You can see that the after even heating to 800 degrees C, the weight loss is the weight of this material is about more than 95%. So only 5% weight loss has been taken place, and this 5% will be due to the removal of this adsorbed water, because silica is hygroscopic substance and it has some it absorbs some water. So after heating it to 800 degrees C, the water molecule has been removed, and the weight loss is only 5%. On the other hand, if you have looked at the B, so this silica surface functionalized with 3-aminopropyl triethoxysilane, which is a silane coupling reagent, and the TGA curve show that the decrease in the weight percent takes place, and at the end of analysis, we get about 60% weight, so 40% weight loss has been taken place. Similarly, another material is also functionalized silica with different ligand, this which is represented by C, and the weight loss percent is more than 60%. It is about 65% weight loss. And similarly for the D, the weight loss is much more. So comparing the TGA curve of different material, you can say that how much strongly the ligand has been attached, what kind of cross-linking has been take place, and what kind of surface functionalization has been take place. And comparing this TGA curve, you can find out, you can differentiate between between the two materials, that either this material is just a base material, or it have attached some different groups, or it have cross-linked group, or it have simply surface functionalized group. And if you look to the bigger caption, you can see that the TGA curve of the pristine silica, the A represents just the pristine silica, and B represent the silica modified with different silane coupling reagent, which I have discussed here, just like the 3-trimethoxysilyl propyl. And another one is about the 3-trihydroxysilyl propyl methyl phosphonate group. So comparing the TGA curve of different surface functionalized silica, you can find out the difference between them. The major weight loss of the pristine silica nanoparticle, the curve A, which correspond to about 9% occur in 2 temperature range, and this weight loss is only about the loss of water molecule. Similarly, the first weight loss is observed at the range of 50 to 150 degrees C, owing to evaporation of physically dissolved waters on the silicon nanoparticle surface. So these are the discussion about which I have already discussed in the previous slide. So this discussion of TGA show that how the what is the effect of temperature change on the material behavior and the weight loss of that material, particularly that either the weight has been lost considerably or only a small amount of weight loss been taken place. And knowing this information, we can discuss the TGA analysis of a sample. Limitation of TGA. There are several limitations of TGA, like the TGA curve are not a fingerprint curve. So it means that even we get a TGA, we cannot 100% believe that that material will be show particular, because TGA is also very sensitive instrument, and with very minor change, the results may be changed drastically. So these are the different parameter will yield different results, and these parameter which affect the reaction rate or the heating rate. Even if you change the heating rate to 1 degree C per minute, so you will get different results for the same material. If you change it to 20 degrees C per minute, you will get different result. If you change to 50 degrees C or 100 degrees C, you will get different result. So heat change is also a great effect. Maximum temperature, how much temperature you have provided. Purge gas, either you have provided nitrogen gas or air, the results will be different. The sample mass and morphology, shape of the sample can also affect. And the pen material, the shape, the size, this is the the material in which we put the sample inside the furnace. So the shape, the size of the material also affect your results. So it means that these results are not 100% accurate. These are not truly representative to our fingerprint. Now I have given one example here. Let's suppose we have provided a material, and the material is heated to 650 degrees C at the rate of 20 degrees C per minute in nitrogen. So you get the TGA curve, and which is marked in a blue line. And if you look toward if the material is heated at 80 degrees C and air, then the TGA curve will look different. So it means that you can check, if you check one material at what keeping one kind of parameter and what temperature, then you will get one kind of result. But if you change the operation condition, so you can get different results. So always, if you want to compare materials with each other, so you have to keep this parameter constant, and you should not change this parameter. That only in that case you can compare the properties of these two materials. Similarly, we have the TGA curve of these three TGA curve. One is heated at nitrogen at 650 degrees C, another and then cooled down at 500 degrees C, and another heated at 800 degrees C. Now this same parameter has been applied here, like heating at and nitrogen at 650, cooling back to 500 in nitrogen, and heating an air at 800 degrees C. But now we have changed the temperature, the rate of the this, like for this curve, we have used 1 degree C per minute. Here we have used 20 degrees C per minute, and for the green curve we have used 100 degrees C per minute. Now look here, the decomposition rate and the curve are looked different from each other, and this is the limitation of the TGA, that even we have carried out very small change, like the change in temperature we have changed from 1 degree C, 20 degree C, and 100 degree C, and you can see the curves look very different from each other. Even the operation conditions are same, like heated up at 650 degrees C in nitrogen, and cooling back at up to 500 degrees C in nitrogen, and heating back in air. But the rate of temperature change has been per unit time has changed, and now you can see the curve has been changed drastically. Another limitation is different parameter will give you different results, limited to quantification of the major part of a sample. We cannot quantify major part of the sample, and so some kinds of material like a flame retarder or anti-accident material, it cannot be quantified typically. Sometimes overlapping or decomposition, we get overlap peak. Multiple part with similar decomposition temperature change can overlap with each other, and it is difficult to interpret these results. And secondary means of material identification mean that we should not only rely on TGA results, we should also use different results like FTIR or DAC combined with TGA. Then we can compare. So TGA only give us it give us valuable information, but we should not 100% rely on TGA. We should also use other analytical technique, other characterization technique, which give you accurate information. We have prepared a material, and only on the basis of TGA we cannot 100% characterize that material, although TGA give us the important and valuable information. If you have any questions, you can ask.
Thank you so much, sir, for delivering your lecture. It's time for some questions. If any participant has any question, then you can raise your hand and ask your question one by one. It seems like there is no question. So, I thank you again for delivering an informative lecture and sparing your time for the IM group of researchers. Thank you for being with us.
Thank you so much.
I
Thank you.
have a question.
All right, you may ask.
Sir, how quantitative analysis performed by DSC?
Sorry, can you ask your question again?
How quantitative analysis performed by DSC?
Using DSC, we cannot properly quantify material totally. Just I have told you that these are just a kind of technique which can be used combinedly. But if you look toward the peak area, you can find out that material we have compared to the same material, and we get the intensity of the peak can give us some information about the quantity of the material, but it is not exactly 100% quantification results, which we cannot obtain using DSC.
Okay, sir. So actually, TMA is not using for quantitative analysis, but it is also not a fingerprint. So we can say that okay, TMA we cannot use for qualitative analysis.
As I have told you that like for the analysis of a material, we are using a variety of technique, and every technique give us specific information. So mostly these thermal analysis like TGA or this DAC or TMA, mostly they are used for the analysis of polymer, and they give us information about like the glass transition temperature, their melting temperature, and their decomposition. This kind of behavior can be checked using this one. So if you want to find out other information, just like if you want to find out the functional groups, then definitely you have to go for other like the spectroscopic technique, like FTR or NMR. If you want to find out what is exactly inside that material, then you choose the NMR. So there are a lot of techniques, and every techniques is specific for specific material. So mostly these thermal analysis are used for the polymeric material, for the analysis of these material to find out some failure or defects and give us some kind of information, but not total information which we want.
So we can by TMA using we can analysis water content, moisture analysis by this.
Yeah, exactly. We can find out the moisture content, water analysis, and some kind of like the degree of mineralization, decomposition, and so on.
Okay, sir. So these techniques have any application in pharmaceuticals?
Yeah, they have these techniques are also used in pharmaceutical industry for find out the moisture content and some kind of this like um, and different industry it can be used particularly to find out the moisture content of drugs and pharmaceutical. These are important to find out how much is the moisture content.
Sir, in
Also to
pharmaceuticals,
find out the active ingredient, how much the active ingredient is found in that particular drug in addition to stabilize.
sir, in pharmaceutical industry, we have an instrument moisture analysis. There is only upper limit of for temperature is 105 Celsius. So we can say that that is the TGA.
No, no. This like the moisture content analyzer. Yes, you said that we have only the temperature limit up to 105 degrees, and we know that the boiling point of water is 100 degrees C. So that particular instrument is only suitable for finding out the moisture content. And when you heat a sample up to 105 degrees C, all of the water molecule will evaporate, and you will get a dry sample and dry weight of the sample. That is not a DSC. But DSC also give you the information about the water content, but the the moisture analyzer machine cannot be, you cannot call it the DSC because that using DSC you can use high temperature and you can use different types of sample, particularly polymer, their decomposition and their recooling or crystallization and so on.
All right. I think
Okay, thank you, sir.
thank you, sir, for answering the questions.
Thank you so much. Thank you.
I think this workshop is really very significant because these characterization techniques are the backbone of research, but are not properly taught at any university. And especially early career researchers always find it difficult to interpret and instrumentation of the characterization techniques. That's why the IM group of researchers decided to bring it to you. So now, Dr. Adnan.